Section 14 of the ABC of Relativity by Bertrand Russell. This LibriVox recording is in the public domain. Chapter 14. What is Matter? The question, what is matter, is of the kind that is asked by metaphysicians and answered in vast books of incredible obscurity. But I am not asking the question as a metaphysician. I am asking it as a person who wants to find out what is the moral of modern physics, and more especially of the theory of relativity. It is obvious from what we have learned of that theory that matter cannot be conceived quite as it used to be. I think we can now say, more or less, what the new conception must be. There were two traditional conceptions of matter, both of which have had advocates ever since scientific speculation began. There were the atomists, who thought that matter consisted of tiny lumps which could never be divided. These were supposed to hit each other and then bounce off in various ways. After Newton, they were no longer supposed actually to come into contact with each other, but to attract and repel each other, and move in orbits around each other. Then there were those who thought that there is matter of some kind everywhere, and that a true vacuum is impossible. Descartes held this view, and attributed the motions of planets to vortices in the ether. The Newtonian theory of gravitation caused the view that there is matter everywhere to fall into discredit, the more so as light was thought by Newton and his disciples to be due to actual particles traveling from the source of the light. But when this view of light was disproved, and it was shown that light consisted of waves, the ether was revived so that there should be something to undulate. The ether became still more respectable when it was found to play the same part in electromagnetic phenomena as in the propagation of light. It was even hoped that atoms might turn out to be a mode of motion of the ether. At this stage, the atomic view of matter was, on the whole, getting the worst of it. Leaving relativity aside for the moment, modern physics has provided proof of the atomic structure of ordinary matter, while not disproving the arguments in favor of the ether, to which no such structure is attributed. The result was a sort of compromise between the two views, the one applying to what was called gross matter, the other to the ether. There can be no doubt about electrons and protons, though, as we shall see shortly, they need not be conceived as atoms were conceived traditionally. As for the ether, its status is very curious. Many physicists still maintain that without it, the propagation of light and other electromagnetic waves would be inconceivable. But except in this way, it is difficult to see what purpose it serves. The truth is, I think, that relativity demands the abandonment of the old conception of matter, which is infected by the metaphysics associated with substance, and represents a point of view not really necessary in dealing with phenomena. This is what we must now investigate. In the old view, a piece of matter was something which survived all through time, while never being at more than one place at a given time. This way of looking at things is obviously connected with the complete separation of space and time in which people formerly believed. When we substitute space-time for space and time, we shall naturally expect to derive the physical world from constituents which are as limited in time as in space. Such constituents are what we call events. An event does not persist and move like the traditional piece of matter. It merely exists for its little moment and then ceases. A piece of matter will thus be resolved into a series of events. Just as, in the old view, an extended body was composed of a number of particles, so now each particle, being extended in time, must be regarded as composed of what we may call event particles. The whole series of these events makes up the whole history of the particle, and the particle is regarded as being its history, not some metaphysical entity to which the events happen. This view is rendered necessary by the fact that relativity compels us to place time and space more on a level than they were in the older physics. This abstract requirement must be brought into relation with the known facts of the physical world. Now, what are the known facts? Let us take it as conceded that light consists of waves traveling with the received velocity. We then know a great deal about what goes on in the parts of space-time where there is no matter. We know, that is to say, that there are periodic occurrences, light waves, obeying certain laws. These light waves start from atoms, and the modern theory of the structure of the atoms enables us to know a great deal about the circumstances under which they start and the reasons which determine their wavelengths. We can find out not only how one light wave travels, but how its source moves relatively to others. But when I say this, I am assuming that we can recognize a source of light as the same at two slightly different times. This is, however, the very thing which had to be investigated. We saw, in the preceding chapter, how a group of connected events can be formed, all related to each other by a law, and all ranged about a center in space-time. Such a group of events will be the arrival, at various places, of the light waves emitted by a brief flash of light. We do not need to suppose that anything particular is happening at the center. Certainly, we do not need to suppose that we know what is happening there. What we know is that, as a matter of geometry, the group of events in question are ranged about a center, like widening ripples on a pool when a fly has touched it. We can hypothetically invent an occurrence, which is to have happened at the center, and set forth the laws by which the consequent disturbance is transmitted. This hypothetical occurrence will then appear to common sense as the cause of the disturbance. It will also count as one event in the biography of the particle of matter which is supposed to occupy the center of the disturbance. Now we find not only that one light wave travels outward from a center according to a certain law, but also that, in general, it is followed by other closely similar light waves. The sun, for example, does not change its appearance suddenly. Even if a cloud passes across it during a high wind, the transition is gradual, though swift. In this way, a group of occurrences connected with a center at one point of space-time is brought into relation with other very similar groups whose centers are at neighboring points of space-time. For each of these other groups, common sense invents similar hypothetical occurrences to occupy their centers, and says that all these hypothetical occurrences are part of one history. That is to say, it invents a hypothetical particle to which the hypothetical occurrences are to have occurred. It is only by this double use of hypothesis, perfectly unnecessary in each case, that we arrive at anything that can be called matter in the old sense of the word. If we are to avoid unnecessary hypotheses, we shall say that an electron at any given moment is the various disturbances in the surrounding medium which, in ordinary language, would be said to be caused by it. But we shall not take these disturbances at what is, for us, the moment in question, since that would make them depend upon the observer. We shall, instead, travel outward from the electron with the velocity of light, and take the disturbance we find in each place as we reach it. The closely similar set of disturbances, with very nearly the same center, which is found existing slightly earlier or slightly later, will be defined as being the electron at a slightly earlier or slightly later moment. In this way, we preserve all the laws of physics without having recourse to unnecessary hypotheses or inferred entities, and we remain in harmony with the general principle of economy which has enabled the theory of relativity to clear away so much useless lumber. Common sense imagines that when it sees a table, it sees a table. This is a gross delusion. When common sense sees a table, certain light waves reach its eyes, and these are of a sort which, in its previous experience, has been associated with certain sensations of touch, as well as with other people's testimony that they also saw the table. But none of this ever brought us to the table itself. The light waves caused occurrences in our eyes, and these caused occurrences in the optic nerve, and these, in turn, caused occurrences in the brain. Any one of these, happening without the usual preliminaries, would have caused us to have the sensations we call seeing the table, even if there had been no table. Of course, if matter in general is to be interpreted as a group of occurrences, this must also apply to the eye, the optic nerve, and the brain. As to the sense of touch when we press the table with our fingers, that is an electrical disturbance in the electrons and protons of our fingertips, produced, according to modern physics, by the proximity of the electrons and protons in the table. If the same disturbance in our fingertips arose in any other way, we should have the same sensations, in spite of there being no table. The testimony of others is obviously a second-hand affair. A witness in a law court, if asked whether he had seen some occurrence, would not be allowed to reply that he believed so because of the testimony of others to that effect. In any case, testimony consists of sound waves and demands psychological as well as physical interpretation. Its connection with the object is therefore very indirect. For all these reasons, when we say that a man sees a table, we use a highly abbreviated form of expression, concealing complicated and difficult inferences, the validity of which may well be open to question. But we are in danger of becoming entangled in psychological questions, which we must avoid if we can. Let us therefore return to the purely physical point of view. What I wish to suggest may be put as follows. Everything that occurs elsewhere, owing to the existence of an electron, can be explored experimentally, at least in theory, unless it occurs in certain concealed ways. But what occurs within the electron, if anything occurs there, it is absolutely impossible to know. There is no conceivable apparatus by which we could obtain even a glimpse of it. An electron is known by its effects. But the word effects belongs to a view of causation which will not fit modern physics, and in particular will not fit relativity. All that we have a right to say is that certain groups of occurrences happen together, that is to say, in neighboring parts of space-time. A given observer will regard one member of the group as earlier than the other, but another observer may judge the time order differently. And even when the time order is the same for all observers, all that we really have is a connection between the two events, which works equally backwards and forwards. It is not true that the past determines the future in some sense other than that in which the future determines the past. The apparent difference is only due to our ignorance, because we know less about the future than about the past. This is a mere accident. There might be beings who would remember the future and have to infer the past. The feelings of such beings in these matters would be the exact opposite of our own, but no more fallacious. The moral of this is that if an electron is only known by its effects, there is no reason to suppose that anything exists except the effects. Insofar as these effects consist of light waves and other electromagnetic disturbances, we may say that what is called empty space consists of regions where these disturbances are propagated freely. Every such disturbance, we find, has a center, and when we get very near the center, though still at a finite distance from it, we find that the law of propagation of the disturbance ceases to be valid. This region within which the law does not hold is called matter. It will be an electron or proton according to circumstances. The region so defined is found to move relatively to other such regions, and its movements follow the known laws of dynamics. So far, this theory provides for electromagnetic phenomena and the motions of matter, and it does so without assuming that matter is anything but systems of electromagnetic phenomena. In order to carry out the theory fully, it would no doubt be necessary to introduce many complications. But it seems fairly clear that all the facts and laws of physics can be interpreted without assuming that matter is anything more than groups of events, each event being of the sort which we should naturally regard as caused by the matter in question. This does not involve any change in the symbols or formulae of physics. It is merely a question of interpretation of the symbols. This latitude in interpretation is a characteristic of mathematical physics. What we know is certain very abstract logical relations, which we express in mathematical formulae. We also know that at certain points we arrive at results which are capable of being tested experimentally. Take, for example, the eclipse observations by which Einstein's theory as to the bending of light was established. The actual observation consisted in the careful measurement of certain distances on certain photographic plates. The formulae which were to be verified were concerned with the course of light in passing near the sun. Although the part of these formulae which gives the observed results must always be interpreted in the same way, the other part of them may be capable of a great variety of interpretations. The formulae giving the motions of the planets are almost exactly the same in Einstein's theory as in Newton's, but the meaning of the formulae is quite different. It may be said generally that in the mathematical treatment of nature, we can be far more certain that our formulae are approximately correct than we can be as to the correctness of this or that interpretation of them. And so, in the case with which this chapter is concerned, the question as to the nature of an electron or proton is by no means answered when we know all that mathematical physics has to say as to the laws of its motion and the laws of its interaction with the environment. A definite and conclusive answer to our question is not possible just because a variety of answers are compatible with the truth of mathematical physics. Nevertheless, some answers are preferable to others, because some have a greater probability in their favor. We have been seeking in this chapter to define matter so that there must be such a thing if the formulae of physics are true. If we had made our definition such as to secure that a particle of matter should be what one thinks of as substantial, a hard, definite lump, we should not have been sure that any such thing exists. That is why our definition, though it may seem complicated, is preferable from the point of view of logical economy and scientific caution. End of section 14.